Okay, first of all, I would like the organizer for this very nice conference. And yeah, today I'm going about talk about several works of me and my collaborators. They are Professor Sun Singh at Hanyang University, Korea, and also Dr. Wenhe Cai at Shanghai University, and Dr. Yang Loin at the University of Göttingen, and my three PhD students, Yuan Haiming, Cao Shizheng, and Zhang Qinghao. This is some reference for this talk, yeah, by our group. So first of all, I would like give you some background information and the main motivation for this talk. In fact, Professor Chen Peng already presented to you a lot of information about SYK. Of course, we have reason to study SYK model. Here, we mainly focus on the thermal and dynamical effect of some deformed SYK. For example, non-Hermitian SYK models. We try to find how the non-Hermitian deformations alter the thermodynamics and dynamic structure of a coupled SYK system. Then we turn to the post-skipping phenomena, which in the two-dimensional JT gravity side and SYK side. And also we trying to find the precise correspondence between two-dimensional gravity post-skipping and the complex. Also in not only in ADS, but also for the theta gravity and double scaled SYK model to find some precise correspondence. And then we turn to the replica problem for n SYK models by using the supersymmetry metric. We'll present the discussion and conclusion of this talk. Yeah, we know that for four-dimensional gravity, there's the big problem with this four-dimensional Einstein-Hilbert action is that it's non-renormalizable because the perturbative expansion generates infinite quantum terms. Also, the Newton coupling constant has negative mass dimension. So it makes things difficult to do some predictive calculation at high energy. So for this reason, if we go back to two-dimensional gravity, then we can try to see some low-dimensional toy model, for example, JT gravity, and also there's a field theory duality of these JT gravities is SYK models. So yeah, this is a reason. But also we can see that as well, JT gravity, the action, in fact, very simple. It's a topological gravity coupled to a dilaton field. And it has ADS2 solutions with boundary dynamics. It's UV finite and it's analytically solvable. This two-dimensional JT gravity, in fact, is closely connected to SYK model because the low energy limit of SYK to match the JT boundary dynamics, and also the Schwarzschild action emerged in both setup. So we all know the story about SYK models is proposed by Kadyrov in 2015. This model is analytically solvable in the large limit, and also for this green function when the melodic diagram contribute to the green function. So if in the low energy limit, we can ignore this term. So this makes the Schrödinger-Dyson equation is easier to solve. And also there is emergent conformal symmetry. And the effective action for SYK model and also the boundary nearly at S2 is use the Schwarzschild action. This is just some background information. So let's turn to the our work. We proposed non-Hermitian two coupled SYK models and trying to find to see the thermodynamics and also the dynamic property of the non-Hermitian two coupled SYK model. For non-Hermitian system, we have a reason. The reason to study this is simply because for non-Hermitian system, it emerged when considering non-conserving probability influenced by external degree of freedom beyond the Hilbert space. Also, if there is PT symmetry, then the Hamiltonian can be, it has a real spectral, So it's still, very good property. And also here, we just developed the previous proposed non-Hermitian physics to SYK models and trying to find the thermodynamic and the dynamic effect. So for the two coupled SYK models, we introduce the Hamiltonian in fact as follows. Here is the C dagger is a direct operator. So here we include interaction term. This interaction term, in fact, makes the Hamiltonian non-Hermitian. Without this interaction term, this Hamiltonian is still a Hermitian case. So, and here the parameter alpha, in fact, controls the strength of non-Hermitian entity. And the coupling constant mu controls the coupling strength of two SYK sites. So this is the Hamiltonian. So let's see what happened to the energy spectrum of this Hamiltonian. In fact, this Hamiltonian can be obtained by doing self-similarity from the Hermitian SYK models. So in fact, we expect the energy spectrum to be real. And then we did some calculation. But before that, let's provide you with some total picture or a physical picture of the Hamiltonian we are discussing. So the left finger represents some transversal wormhole, and the right one is represents some two disconnected black holes. And the middle one is in fact it represents unstable geometry connecting two SYK sites. So here we have different colors here for the left one and the right one because we have a non-Hermitian parameter. The non-Hermitian parameter, in fact, makes this left and right to be a symmetry. And also we can, in fact, later we can see that the dynamics from the left to right and from right to left, in fact, is different. It depends on the non-Hermitian parameter alpha. So, but in fact, if alpha go to 0, the phase diagram can recover that of the Mendelssohn Q model. Here we present the numerical calculation for the energy spectrum we can see that in fact, no matter how big is alpha, the energy of this system is always a real number. Yeah, it does not depend on the non-Hermitian parameter. Also, yeah, for this non-Hermitian case, in fact, we need introduce by orthogonal set because the left set and the right should be different. But here we impose the constraint on this the basis state, and we ask the eigenstate satisfy this relation, so that the corresponding ground states of the coupled Hamiltonian can be written in this form. If one go back to a Hermitian case, all these A tilde, B tilde, C tilde, and D tilde should be equal to 1. But here for non-Hermitian case, A tilde, B tilde, C tilde are controlled by the non-Hermitian parameter alpha. Here we also impose the constraints on the system so that the system has the ground state energy, same as the Hermitian case. And also the ground states should satisfy this relation. And by considering this constraint, we can find that this 4 coefficient satisfy the relation as follows. And also, also we can find the degree of entanglement of the ground states is in fact is independent of the non-Hermitian parameter alpha. So so the interesting thing is to see what happened for the low energy effective action. By introduce the retarded grain function as follows, and we can in fact write down the Schwarzschild action. And here also we can introduce a conserved charge, not charge of the system. And then we can, in fact, we can derive the action of, Because we are considering, in fact, complex, complex. But here the chemical potential is 0. Yeah, 0. But still there are conserved quantities here. So, right. Mm-hmm.
The last term at page. So the first one is the final temperature Quartzian.
Yes. Yes. The third one is contributed by the coupling between 2 SYK. This makes the connection between 2 SYK become transversal because of the third term. Right. Yes. Also, this all does not depend on the non-Hermitian parameter alpha. Yeah, for this effector action, in fact, this effector action describes non-relativistic particle in a potential. Also, this effector action independent of the non-Hermitian parameter alpha. So, in fact, we can plot this potential as a function of the dilatant field. We can find this, this potential very similar to the in ordinary thermodynamics is Van der Waals gas vapor phase transition. In fact, this means the system in fact has first order phase transition. Then we do some numerical calculation for this system. For this figure, we can see that at higher temperature, in fact, this is for off-diagonal term. All of these are this case is gapless. It is two separated black hole case. No wormhole here. But if temperature is low enough, we can see that there is a gap open here because this dashed line and this line, the gap here. This means the wormhole open in this system. Here this is alpha is 0.3, this is alpha 0.2. But if alpha is very big, we can see that off diagonal green function dominate for larger alpha. For both alpha to be positive and also negative, we can see they are dominant. But even though the green function has alpha dependent, but we found that the free energy does not depend on the non-Hermitian parameter alpha. We can see that for here the wormhole phase and here the black hole phase, as the coupling between two SYK models increase, this phase transition point shift to right. So yeah, this two figures just show us that there no alpha dependence. This is for thermodynamics calculation. But if we consider the dynamics, we can see that in fact the dynamics of this system in fact is influenced by the non-Hermitian parameter alpha. Because we have wormhole, we can also in fact we have mainly two phases. This one phase is wormhole phase, another phase is the black hole phase. So we can see that for the off diagonal green functions for this diagram shows for the black hole phase, the off diagonal green function decay with time very quickly. But if there is a wormhole, for example, the wormhole excitation from left to right, it means that it can be transformed from left to right. And here, this diagram shows us that there is the amplitude effect is non-zero. And also, we found that alpha symmetry of the green function here is the diagonal GR and GLL and GR are equal. But for the off diagonal case, there is alpha dependence. So this is for the revival dynamics. It means the signal can be sent from the left one to from the left SYK to the right SYK, and also they are in fact the left right and the right left. In fact, they are not symmetric, not symmetric. And also, we can calculate the spectral function as a function of the frequency, and we can see that the peaks distribution in fact depend on the alpha. Here is for black hole phase, and the right one is for the wormhole phase. We can see that for one case, the peaks in fact different from the black hole phase, in fact. And also for the transmission amplitude, for different temperature, we can see that for alpha even is 0.1. In fact, the off-diagonal transmission effect dominates in the particle transmission between left SYK to right SYK. So here, let's briefly summarize. So we found that the non-Hermitian does not change the thermodynamic of the coupled SYK model, but it do affect the dynamics of coupled SYK. And also the green function obeys this relation. And this in fact this relation implies that the directional state transfer bias between left one and right one if we introduce the alpha dependence. This is the first part of my talk, and then let's see another phenomenon interesting to discuss is the post-clipping phenomenon. In fact, we calculated post-clipping in the two-dimensional JT gravity and also on the SYK side, and trying to find something, the correspondence between these two models. Let's first summarize the main result of this part. In fact, here we found that there is one-to-one mapping between the post-skipping point in JT gravity and the SYK model. And for complex SYK, in fact, we found that this is the complex SYK asymmetry parameter epsilon. In fact, it corresponds to the chemical potential shift at the black hole event horizon. This is a very interesting result. In fact, also we extend this work to consider the post-skipping structure in the two-dimensional de Sitter spacetime. We found that that the post-skipping in the Sitter two-dimensional de Sitter spacetime has one-to-one correspondence to the infinite temperature double-scaled SYK model. Here is just, in fact, we are not know exactly what the behind the physics, but mathematically there are very good correspondence between those two different systems. Before going on, let's first say something about what is post-skipping. In fact, a generic retarded green function we can write in this form. If there is post-skipping, it means that both this B and A function should be 0 at some special point. So this means if this 0 over 0, this means that a retarded green function is U defined. So we need trying to find some trying something else to avoid this point. In fact, this point we call it a post-skipping point. To find those post-skipping points on the gravity side, we can expand the field expansion as Taylor series as follows, and we can obtain the identical equation from the bulk equation, and we can find that in fact the two solutions, and in fact the post-skipping phenomena appear because we have there is no unique incoming mode at the black hole horizon at those post-skipping points. This, in fact, leads to the non-uniqueness of the green function on the boundary. Yeah. This means that two incoming solutions correspond to non-uniqueness of the green functions. This is the reason why post-skipping happens. And also post-skipping, there's some people discuss about this post-skipping. It's closely related to the quantum chaos, but in fact, post-skipping, in fact, independent of the quantum chaos, because there are many post-skipping points that not included in quantum chaos. So for JT gravity, we just we write down the action and consider the Schwarzschild-like solution in this JT gravity, and we consider Klein-Gordon minimum coupled Klein-Gordon equation in this JT gravity, and expand the wave function near the event horizon. We can there's some. We can expand the equation of motion, and we can read off the post-skipping point from the from this metric from this metric, and we can find that the post-skipping in fact is this point here. Here is two-dimensional case. So we regard the mass of the Klein-Gordon equation to be as effective momentum, because in two-dimensional case we don't have the degree of freedom of momentum, and then we can read off those post-skipping point as different dimension as follows. This is on the JT gravity side, and also we can do the similar calculation on the asymptotic boundary, and we can find that this at the asymptotic boundary, the retarded green function has this forms, and we also can read off the post-skipping point as follows. So in fact, this matched with near horizon post-skipping point. This is a story on the JT gravity side, but if we switch to the SYK side, we can consider the Majorana SYK models, and also write down the Hamiltonian of the Majorana Hamiltonians, and we can see that for this Majorana SYK model, the effective action has two terms contribution: the conformal field series contribution and the conformal field series symmetry breaking contribution. And here the operator OH in fact is a bilinear primary single trace operator which has scaling dimension H. Later we can see that this scaling dimension H will correspond to the scalar dimensions. We will try to here we will try to build the gravity theory scalar field, and also the boundary field theory. We have the scalar operator O, and then we can see that for the SYK, the green function can also written in two parts: the conformal part and the non-conformal part. For the non-conformal part, in fact, we can see that the solution, in fact, is it has this form. So for this retarded gain function, in fact, that if we shift the frequency with a constant, and then very soon we can find that we can obtain also the postcaping for this SYK. This the postcaping point, in fact, exactly agrees with the calculation from the two-dimensional JT gravity side. And also for alternative quantization, also we can find there is the exact mapping between two systems. This is a comparison of post-schemic point in JT gravity and the Majorana SYK models. We can see they have exact matching between each other. For charged JT gravity, we should, in addition to the metric, we can consider the gauge field near the horizon. And we can say that this epsilon, in fact, is constant related to the chemical potential. And also for the retarded gain function, we need to do a shift to the retarded gain function to obtain the location of postcaping point. And later we can see that the same thing should be do for the complex SYK, but the shift parameter is different. For complex SYK, the Hamiltonian can be write down as this form. Here we have actual this second term, in fact, is chemical potential term. Here we introduced a conserved U1 density. And we can see that the retarded gain function of the complex SYK, in fact, is given as this form. Here, this capital E, in fact, controls the particle asymmetry. We call it particle asymmetric parameter. We can see that a postcaping point happened at this point. So this means we also need to do a shift to the retarded gain function so that the charged SYK models the postcaping point can be a match with the charged black hole gravity. So we can summarize here for the parameter of the black hole can be interpreted as the spectral asymmetric parameter capital E. So the postcaping point show good agreement with each other, and also for the complex SYK model, the variable H minus corresponding to delta minus. It means that the alternative quantization also they match with each other. This is for the This is for the JT gravity, which has ADS2, nearly ADS2 geometry. In fact, if we consider the theta, two-dimensional de Sitter spacetime, and also we find that the corresponding postcaping point, in fact, is related to the double skewed SYK model. So for postcaping in de Sitter gravity, scalar and in fact Fourminic field in fact also exhibit the postcaping frequency. So this postcaping frequency in fact is all in the upper half plane. And to find the field theory due of this postcaping, in fact we should consider the double skewed SYK. at infinite temperature. And yeah, in fact, we can find there's at least at the mathematical level there one-to-one between the theta SYK and then double skewed SYK. So here we consider the scalar field in for the theta space, and also here we know that the cosmic horizon is located at this place, and the global temperature is given by the following. And also we did the same calculation anti the theta case, and we can also obtain the post-caping point near the horizon. We can see that all this post-caping the sign is positive. It's in fact different from the ADS case. And then for double scaled SYK, let's see, we also start from the original N Majorana formulas, and in the double scaling limit, we should define, in fact, above the infinite temperature, we should define an effective temperature. And this effective temperature is finite as beta goes to 0. And we also can find that the 2-point function of double scaled SYK at infinite temperature is green function goes like this. Here the data represent the size operator in the double scaled SYK. And here for the double scaled SYK, we can also calculate the post-caping point here. And for integers and half integers, all these post-caping point of the double scaled SYK agrees with those of two-dimensional gravity. This is just the figure to show the blue lines are the plot of poles and zeros of green function in the double scaled SYK. The red point here is intersect with the position of post-caping. So we can find that here they are in fact agrees with each other. So let's briefly summarize the result. The post-caping structure in the theta gravity. It's based this relation. In fact, here the S is a spin. The field spin of the field. So this upside to ADS case. Also, we identify a one-to-one mapping between post-caping point in two-dimensional gravity and the infinite temperature double scaled SYK. Also, we can, in fact, regard the post-caping as a universal check because post-caping can behave as a powerful probe for trivial dualities in both ADS-FT and also the theta correspondence, even the involving non-physics or massless modes. And because I still have time, so I go to the third part of my talk. So previously, we know that for SYK models, it's claimed to be due to a black hole. So in principle, we should be able to give the Page curve from the SYK models. The problem is that if we have arbitrary number of SYK models, the problem is how to solve the replica Hamiltonian and how to do the calculation for arbitrary n copies of the SYK model. So to solve this problem, in fact, we introduce some method by borrowing the method from supersymmetry. Let me show you what happened for the system. For why we consider the n replica, because previously we know some well-known work on P-curve and black hole information paradox. We know that the competing settles in entanglement entropy. They are Hawking settles. For Hawking settles, the quantum gravity effects are neglected. So the radiation entropy in fact increase with time. But for replica wormholes, we should include non-perturbative contribution. This gives you unitary pitch curve. This is already done in semi-classical gravity side. But what happens if we do this calculation on the SYK side? Here we propose that supersymmetry can make the calculation easier. The reason is as follows. For example, if we consider two copies SYK models, the left one and the right one, and we consider the replica copies of this left and right, and we can, after disorder average, we can obtain the effective bilocal interaction terms. This is not hard to solve because it's only two copies, two replica. And also, naturally, the replica average, the disorder average naturally gives us replica wormhole here. But if we want to extend this calculation to arbitrary copies of the Hamiltonian, then we should write down the non-local interaction formula for n discrete replicas. And potentially this interaction generating connected multi-replica geometry in the dual gravity. So this means this interaction term, in fact, lead to replica wormholes, connect n geometries. So the question is how to solve such huge number of replicas. For example, we can consider the 3 replicas and see for each copy we can write down the replica interaction order by order, this diagonal, and the two, just two copies connected. This part is 3 copies connected, and then we summarize. So for this 3 replicas, in fact, is in principle we can solve it by using some numerical calculation. Also, but for analytical calculation, it become in fact very difficult. But if there is some symmetry between the parameters, we can also solve some special cases. But there are still some subtlety here, because for n equal or bigger than 3, we constructing consistent off-shell wormhole configurations become non-trivial. So just solve this special case is not enough. So we should have some method from supersymmetry, in fact. So here is the main difficulty to full understanding of a replica SYK model. The first one is analytical method breakdown for n big or equal to 3 replica because increased complexity of replica wormholes. Also, the path integral fails to capture essential off-diagonal contribution for entropy calculation. Also, there are some generated settles so that the multi-replica wormhole solution complicates the interpretation and also dilute predictive power. So this issue abstract a complete microscopic derivation of the page curve in the N-replica SYK framework. So to make things easier, we should in fact introduce supersymmetry. Here we just introduce N equal to 1 supersymmetry and introduce a supercharge here. And for example, for Q equal to 3, we can write down the Hamiltonian as a square of the central charge, and also this this here the Majorana field and the central charge supercharge satisfying this this relation, and here we have the conjugate bosonic field generated here. And this conjugated bosonic field helps us simplify the calculation. And here we can write down, for example, for the simple case, we can write down the total Hamiltonian as left one, right one, and the interaction term. And this interaction term, in fact, simultaneously introduce interaction between the left one and the right one. So here the coupling constant mu controls the strength of supersymmetric coupling between left and right system. So in fact this Hamiltonian effect is that Madesina Chi models, but here this is bosonic and fermionic field coupling here. So this is just for the example. If we extend this calculation to arbitrary order, then we should introduce recursive formic tension. And also, we should consider the fractal supercharge structure to for the index for the superscript of the supercharge. So the high order supercharge act across multi-layers. And also the supersymmetric algebra produce increasing structured bosonic partners in this case. And then we can expand the Lagrangian layer by layer because we introduce the conjugate bosonic field. So the action receive the contribution from all nested SYK setters. So this by write down this Lagrangian, in fact we have a fractal-like structure in the series space. And also the rich replica entanglement pattern and wormhole connections. Here we give the example for this single layer coupling, just the simple case. This means that there is a projection from the Majorana fermion to the supercharge. Here we have a conjugate field here, But if we have 2 layers, that means that there's a splitting happening between left to right. And if we, this is a chart diagram. If we can extend this diagram to arbitrary levels. Here we just give you some thermal phase diagram of this system. This is for the non-supersymmetric case. We can find that increasing the replica coupling short the phase transition. But if we turn on the supersymmetric coupling, we can find that we have 2 distinct transitions emerging at some immediate the coupling constant. Yeah, also for this means that there are still first order phase transition. And also the critical point of this system happens at the TC is 1.15, and the critical coupling is at 0.3, and also for the this 2 layers, mu c is 0.84. Yeah. This is for thermal phase diagram. We can also, if we consider Lorentz time, we can also evaluate the Lorentz effect action as a function of time. We can find that, in fact, for this system, we have black hole phase and wormhole phase. For black hole phase, we have very quick decay of the perturbation effect. But for wormhole phase, we can see the quantized structure here. Also, we calculated the modular entropy as a function of the replica parameter. We can see that, in fact, the replica parameter plays the role of inverse temperature. If we turn on the supersymmetry, we can see the converge become more smooth. Also, we calculate the entanglement capacity for this system. This finger shows you the no coupling case. For no coupling case, the peak happens as n equal to 5. But for full coupling, we can see that the peak shift left, in fact. This means that the wormhole changed the entanglement capacity, the property of entanglement capacity. If there's half coupling, it means the coupling constant is 0. We can find that, in fact, the competition between 2 settles, wormhole settles and black hole settle has competition. In fact, we can also consider the extended near ADS2 spacetime with jetting gravity. Here we plot here just show how the supersymmetric parameter works here. The inside is just 1 layer. The outside circle is represent 2 layers. Here we can see there is a splitting happens here. But if we expand to arbitrary layers, we can many splitting behavior. And this, in fact, change the Penrose diagram. For example, if M and N are identical, this means this in supersymmetric parametric space, they are they are overlapped. But if they are not overlapped, this means that the Penrose diagram in this supersymmetric space change. So we can see that in the inside, if we send a signal inside, it should be reflect here. But if we send a signal from the middle black line, this signal can transfer to the right middle one. And this means that there's the layer by layer, and also for this case, we can also write down the effective metric for this parent diagram. Okay, let's give you some conclusion, and in this talk we consider non-Hermitian coupled SYK. In fact, this non-Hermitian is in fact the pseudo Hermitian, and also calculate the entanglement influence on the system. And we found that the non-Hermitian affects symmetry breaking pattern, but leaves the spectrum and entanglement endpoint invariant. Also, post-skipping correspondent in near IDS2 and SYK and the theta double-skewed SYK correspondence. In this setup, we replace momentum K by mass to identify post-skipping in 1+1 gravity. And also, we established one-to-one match between post-skipping point of Majorana or complex SYK and omega and the scalar operator in JT gravity on a standard and alternative quantization. Also, we identify a one-to-one mapping between post-skipping point in two-dimensional gravity and the infinite temperature double-scaled SYK model. So this provides some numerical evidence for the theta holograph duality. Also, we developed, we called it a multi-ordered trick for any replica SYK. We introduced a hierarchical framework for exactly multi-replica wormhole solution in the n equal to 1 supersymmetric SYK. We also generalized from 2 to n replica with systematically controlled off-diagonal interaction. Also, we consider the fractal symmetry and super symmetric unification of this system to guarantee that our calculation works. By analyze Lorentz dynamics with emergent superconformal invariance and across replica, we find, in fact, there are two phases, the black hole phase and the wormhole phase. So also, I did not talk much about the super JT gravity. In fact, this n-replica supersymmetric SYK model, in fact, is matched with the super JT gravity. Because I maybe I will show you this part. Also, we computed the entanglement measurement through the exact diagonalization across replica sectors, so that we can build the holographic duality between supersymmetric n-replica to the supersymmetric JT gravity. Okay, so for the future work we want to discuss is the following, because we know that in quantum mechanics there is a well-known theorem. We call it quantum non-collinear theorem. It claims that the unknown quantum state cannot be perfect copy. So here we consider n replica system But in order to make this system works, we need to prepare n identical wormhole replicas. So we need to know the full knowledge of the quantum states. So without the prior information about the quantum states, replica construction in fact violates non-cleaning theorem. So this is still a question to be considered in the future if we do some experiment to simulate black hole evaporation. At least how many copies should we prepare to recover the information? Because field replicas minimize the complexity and the resource requirement. And also small replica numbers risk incomplete information extraction from gravitational path integral. And also, in the future, we can explore the n dependence to see what happened. This is just for the future work. Okay, because of time, thank you. That's all of my talk. Thank you very much.
Okay, thanks for the beautiful talk. Any questions? I have a short question.
Yes.
Whether we can generalize this case, this Replica construction to the high dimension case.
You mean n replicas SYK to high dimensional case?
Yes, yes.
For high dimension case, maybe you can ask Professor Peng Chen. He consider the high dimensional extension of SRK models. In fact, this can be done by using supersymmetry. I think Professor Peng Chen already has several papers on this problem.
SYK, right, which is the theory of reparametrization. But I think Kohler-Jensen lifted this to sort of a 2D theory of reparametrization. So there's a reparametrization field, depends on both time and space. And that's the kind of, in some sense, the lift the ADS2 Schwarzschild duality to ADS3 and some higher dimensional version of the Schwarzschild. And I believe there's a group, I forget all the names, Nelly Calibo, and then maybe Johanna Erminger. I'm not sure. There's a group that produced an SYK model whose the analog of the Schwarzschild limit lands on the Kohler-Jensen higher dimensional Schwarzschild. So I think that theory exists, and one could try to reproduce those results.
Thank you.
Okay.